So the fourth remark is the definition of the function is continuous on a closed interval. Right? So that means the endpoints would be included. So we say a function is continuous on a closed interval if f of x is continuous in the open interval ab. So what is the definition for the continuous in an open interval we have stated here, right? This is the continuous on an open interval. So this is the first thing, inside should be continuous at each point. What about the endpoints? For the left endpoint, you should be right continuous. That means the limit x approaches a plus of f of x equals f of a. For the right endpoint, the function should be left continuous. So the limit as x approaches b minus of f of x should be equal to f of b. So the graph would be looks like this one. So this is AB. At A is a solid point. At B is also a solid point. So you can draw the graph continuously on the whole closed interval AB, right? So the next question is, which functions are continuous functions? So actually, the functions you have learned in your pre-calculus are all continuous functions. And if you have two functions, so how to construct other functions to be a continuous one? To be continuous, if you have f, function g, both functions are continuous functions on certain intervals on the domains are continuous, then you can get this result f plus or minus g. Make an addition of these two functions or make the subtraction of these two functions. These two functions still be continuous function. And if you take the multiplication f of x times g of x, this would be also continuous function on the domain. If multiply by a constant on the function, on a continuous function, which is also a continuous function. If you take the division of these two functions, of course, we should guarantee that g of x will not be equal to 0, right? Otherwise, it is undefined. So this one is also a continuous function. Even more, if you make the composite function of these two continuous functions, this composite function would be continuous function, right? And more, you have the inverse function, right? The inverse function, if it exists, would also be a continuous function on the domain, right? So these are continuous. So addition, subtraction, multiplication, constant multiplication or scalar multiplication, division, composite, or inverse. These operations will make a function still to be continuous function on its domain, on the domain. So you should be careful, should be on the domain, okay? So here you will see this example. So for example, sine of x minus 1 square root. Okay, so this is the x minus 1 is a linear function we have learned in the calculus, right? Sine function is the trigonometric function we have learned in pre-calculus. The square root is also a function we have learned in the pre-calculus, right? You also have some logarithmic function, exponential function. These functions are continuous functions. So the division should be continuous, right? Then we make the composite function. Sine of this function should also be continuous. So this function, so what's the domain? So be careful, we have some restrictions on the domain, right? We should make this function to be defined. So the domain is x should be greater than 0, right? The square root should be greater than or equal to 0, x. But it's in the denominator, so x cannot be 0, so x equals 0, greater than 0. So then we can say this one is continuous on its domain, which is x greater than 0. It's very easy, right? The functions you have learned in the pre-calculus are all continuous functions, except the piecewise function. So here is the theorem. Tells you that if you have two continuous functions, then it's very easy to find the limits for the composite function. So f and g are continuous. Okay, of course there are some other conditions on f of g I don't want to state anymore. It just makes this two composite function to be defined. Okay, then the limit x approaches c of f of g of x, which is, if both are continuous function, we know that this would be the continuous function. Composite would also be a continuous function, right? So this would be the f. You can plug in the limit. Right, which is f of g of c. Okay, so the quick example is the limit x approaches 0 of cosine of sine x over x. Okay, so we know this continuous function, right? This is a composite function, so cosine is a continuous function. And, sorry, this is not a good example. Let's look at another example. Limit x approaches 0 of cosine x squared plus 1. Okay, so this is the continuous function. Cosine x squared plus 1 is also continuous function, so this would be, you can take the limit. Cosine is a continuous function, so we can take the limit inside, and the inside is also a linear continuous function, so this would just be cosine 1. Right, you're plugging 0 here, it would be 1, so it's cosine 1. Let's continue to look at a very important theorem in the calculus, which is called the intermediate value theorem, which is called IVT. It says, suppose f is continuous on a closed interval AB, and at the end point, they take the different values. That means f of A is not equal to f of B. And k is any number between f of A and f of B. Then the conclusion is there exists at least one C in AB, in the closed interval AB, such that f of C will take that number k. Okay, so let's look at the geometric meaning for this one. So you have a function. So the continuous function on AB, right? On AB, this is A, this is B, and here take the value f of A. Here you take the value f of B, It says you pick an arbitrary number between f of a and f of bk here. There exists some c here in AB such that f of c is equal to this number k. At least 1. Okay, maybe 2, maybe 3, but at least 1. So this theorem, the IVT theorem, has many applications for in computer science or in other other courses. Okay, the one application is the bisection method. Another application is the existence of the root. So that means if you have f of x equals 0, can you guarantee this function has the root? We need to use this IVT theorem to get this result. Okay, so if you are interested in these two applications, you can look at your PowerPoint lecture. There are some examples. Okay, we will not focus on these topics.